All right. Well, good morning, folks. Hopefully, you had a chance to watch that video yesterday and get caught up. For those of you folks who were taking the AP exam yesterday, please let me know how it went for you. Come by and stop by after school today if you have a chance, and let me know how it looked, how you felt about it. So please come on by and let me know. Try to get the video watched as soon as you can, because what we'll do is it'll give you some idea of where we're headed with the remainder of the time that we have together. Okay, so let's go ahead then and let me pick up where we left off with yesterday and kind of just quickly review for those of you folks who were not here, and then what we'll do then is we'll continue on. I'm going to try to finish up with this general background information on energy. I want to talk about work and heat and how that's related, how they are related to one another, and how we use that to describe what energy is. Okay? And then hopefully get into the discussion of spontaneity, which I'm going to try to wrap up with tomorrow. Okay, so make sure you keep in mind then on Friday we're going to meet. We'll meet live, so please make sure you make note of that. And during our class period, that way then I'll be able to talk with you about the exam that you will take next week and what you can expect in it, and then take some of your questions in regard to any of the material that we've covered up until this point. Okay, and that you will see on that exam. Okay, all right. So let's go ahead and let's talk about energy here. We talked about the energy with the different forms that energy can take. Okay, and so we talked about the chemical energy, the nuclear energy, sound energy, and we talked about the types of energy that we have as well, because we have then potential energy, kinetic energy. But we talked about then that the energy flow, the direction in which energy flow can be described. If we can define then what the part of the universe that we are examining in terms of energy flow, we refer to that as the system, and then everything else around it is what we refer to as the surrounding. So the nature of the energy flow then is very important for us, because we need to know then whether a particular system requires energy in order for it to function, or in order for it to work. Okay, or does it give off energy? Okay, and so with that said, then we described and we were able to define then what are exothermic and endothermic processes in terms of systems surrounding relationship, which means then which we were able to use then to show then that within any exothermic process, okay, energy is going to flow from the system. So inside this box here is our system. Energy is going to flow out of the system itself, which means then for an exothermic process, the energy change, that is, the energy change is going to be negative. You're going to see an energy change that's going to be less than zero. And we're going to see that in just a moment, that energy can be measured. Energy changes, energy can be measured, and we can describe then the change in energy, which means then that the energy that the system starts out with is going to be greater than the energy that it ends up with. Okay, so therefore, if we take a look at this here, the energy change here that is described is going to be negative, which means then when we talk about enthalpy, when we talk about the heat energy involved with a particular process, or the work energy involved with a particular process, those energies will be negative. Okay, so you have a loss of energy. Okay, so the system here in an exothermic process, you have a loss of energy. Okay, so energy then is going to be lost as the system progresses. Okay, so energy is going to be moving out from the system into the surroundings, and that's going to be for all exothermic processes. Okay, for an endothermic process, then energy is going to be flowing into the system, which means then the system is going to gain in energy. Okay, and so therefore, if you take a look at this for an endothermic process, the gain in energy means then that the change in energy is going to be a positive one, because it will end up with more energy than it started out with. Okay? Now, in all natural processes, it's the loss of energy. That is, the potential energy ends up being lower here. Okay, so we want to talk about this. We have lower potential energy. The potential energy ends up being lower here. The potential energy ends up being higher here. And remember when we talked about this back in chapter 7 and 8, when we talked about the bonding types, all systems want to end up at a lower potential energy. They don't want to be a higher potential energy. And so therefore, for any process that's exothermic, that is going to be what we refer to then as a spontaneous process, favorable, because it will put the reactants, the starting material, the starting components into a lower state of energy. And so again, what I wanted to draw your attention to, and what I want you to think about then, is I wanted you to consider then how water flows down a hill. Water doesn't like to stay at the top of the hill or the top of the water tower. Water wants to move down to its lowest point. Okay. Why? Because that represents the lowest potential energy. Okay. And so chemical processes, all processes in nature are also very much the same way. And that actually gives, will allow us to discuss then the second law of thermodynamics that does talk about how all processes will favor a lower energy state or a more spontaneous or a more, a sporadic, chaotic state. Okay, so we'll talk about that when we get to that in chapter 17. Okay, so this is basically what you have to keep in mind then. For an exothermic process, energy will flow out. For an endothermic process, energy will flow into a particular system. Okay? And so let's go ahead and let's take a look at a couple examples here, and let's apply what we know here about exothermic and endothermic and system surrounding relationships, and apply it to a problem here that would that you could possibly see. Okay? Later on. Okay, and so let's take a look at this. The process that we're gonna look at here. The process that we're gonna examine then is the process of freezing water that freezes. Okay, so the system here. So let's go ahead then. Once we have that, okay, let's go ahead then and let's draw a quick diagram here to indicate then system. And let me go ahead and draw a box really quickly. There's our box here. And so what we're going to do is we're going to represent what's inside the box here as our system. Okay, and everything outside is going to be our surrounding. So the process that we are examining then, folks, the process that we're examining is the freezing of water. That's the aspect of the universe that we are examining. And that represents our system. So we'll write that in here. We'll write then that the system then is the freezing of water, which in chemical terms, if you want to think about that, is the taking water in the liquid state and changing it into water in the solid state. Okay, so with that said then, if this is our system, if this is the system that we're looking at, okay, does energy flow into, which is what endothermic is, or does energy flow out of that particular, for this particular process? Well, let's consider this. What type of energy is involved in freezing or melting? Then that then is going to be heat energy. Okay, so heat energy is what we're going to look at then. Okay? So when an object, when a substance freezes, does heat flow out or does heat flow in? That means then think about this. Do you have to lower the temperature or do you have to increase the temperature in order to get water to freeze? Well, you have to drop the temperature. And remember, temperature is just simply a measure of heat energy. It's just a measure of relative heat energy, which means then if you have to drop the temperature here, you have to drop the temperature here to freeze the water, okay? That means then you are dropping the heat energy. You are removing heat energy, which means then if you want to consider this then, heat energy is going to flow out. Heat energy is going to flow out of the system. The system has to have a lower temperature in order to get liquid water to freeze into solid water, into ice. And so therefore, if heat is flowing out, if energy is flowing out, this process then is going to be an exothermic process. Okay, so it's an exothermic process because energy has to flow outward. Okay, all right. Let's do another example here. Let's do another example. Let me go ahead and clear this out. Okay, let's do another example here, and let's take a look at this. Okay. All right. So what I'd like you to do is take about 2 minutes. Okay. And what I'd like you to do is identify for each one of these processes here, whether the process is an exothermic or endothermic process. And what I'd like to do then is I want you to identify the system and what is the system that we're examining here. Okay. And then identify whether it's exothermic or endothermic. Take about a couple minutes to get this done, folks, and then we'll go over it together, okay? All right, let's go ahead and take a look at the first one. I'm only gonna draw the box of the first one. Okay, so let's go ahead and take a look at the first one. Let's draw the box for it to represent then the exothermic, endothermic nature, okay? I'm sorry, to identify the exothermic, endothermic nature of this process. Okay, so let's go ahead and do this. Okay, so there's our box, okay? So there's our box. What goes inside this box then, folks? So your hand gets cold whenever you touch ice. Okay, your hand gets cold as whenever you touch ice. So this is your hand. Your hand is the system. That's what we're gonna look at there. Okay, so when your hand gets cold, whenever you touch it, you want to consider this then. And so when you're talking about cold, we're talking about, again, heat energy here. Okay, so let's go ahead then and ask ourselves this question. Okay, so we're looking at heat energy. Your hand has heat energy in it. So when it gets cold, does that mean then heat flows out of your hand or heat flows into your hand? Okay, well, let's consider this. If your hand gets cold, heat has to flow out from your hand into the ice. The ice then represents the surroundings and whatever else you have there. Okay, so therefore, if heat is flowing out of the system here, this system then is going to be this. Your hand is going to be then an, we'll do this, exothermic process. So the very first process here is going to be an exothermic process. Okay, let's go ahead and do the same thing for the second one. Let's go ahead and do the second one. I'm going to leave the box here. Let me go ahead and erase inside the box really quickly. Okay, let's go ahead and erase this. All right. So for the second one, then let's consider this. Okay, what is the system in the second one? Well, it's the ice then. The ice is the system this time. Okay, so we have ice here. Okay, ice is the system this time. Okay, and so we were talking about the warming of ice. We're going to warm up the ice, okay, when you touch it. So this time the ice is the system here. And so the question then is, if you consider this, okay, so the ice has a certain amount of heat. Remember, everything has a certain amount of heat energy, and that's what you want to keep in mind. Why? Because everything is in motion. Okay? Everything is in motion. Ice is cold, but it has a relative amount of heat because the particles, the water particles that are the solid, they are moving inside the ice itself. So ice does have heat energy. Everything cold has heat energy as well. It's just when you touch ice, okay, it has less heat energy than your hand. And so therefore, in this particular example, and part B here then, the system is the ice. The surrounding then is going to be your hand. The surrounding is going to be your hand. So the question then is, does heat flow into the system or does heat flow out? Well, we're talking about ice getting warmer. So heat then flows into the system. And so if heat flows into the system, then what we have then is an endothermic process. Okay, heat flowing in is endothermic, heat flowing out is exothermic. Okay, let's do a couple more here. Let's do a couple more here together. Okay, let's do a couple more here together. Okay, I'm going to go ahead and erase these here so we can use this box again. Okay, all right. So let's go ahead then. Let's identify what's in this box. Okay, what is the system for the part B? Okay, water boils in a kettle being heated on a stove. Water here is your system. Okay, so here the system, if you want to take a look at it, this is going to be water in the liquid state transitioning to water in the gas state, the process of boiling. Okay, so this is the process of boiling that we were considering here. All right, so we have every system has a certain amount of heat, and we're going to learn this in chapter 17, that heat is everywhere, folks. Heat is everywhere, even in deepest, darkest space, even in the coldest environments, anywhere in the universe, heat is present. Okay? Heat is a present, and it's a signature. Everything has a certain heat signature associated with it. I'm not an astrophysicist. I can't speak for black holes or whatnot, but from what we know then, heat is present in every object. Okay? Heat is present in every object. Okay? All right, so here we have a system. Our system then is water boiling. Okay? So then therefore the question then is, if you boil water, okay, if you boil water, does the system then take in heat or does it lose heat? Okay? Well, obviously when you boil water, you have to bring heat into the system. You have to heat up the water in order to get this done. So therefore, very much like with the melting of ice, okay, it has to absorb heat. So therefore, this is an endothermic process. Okay, remember what we did in the previous example was that we were talking about the freezing of ice, taking liquid water and making the solid. That was an exothermic process. Okay. All right, so with the remaining two then, water vapor then, the system then in this last, fourth example here is going to be the water vapor itself condensing, which is going to be taking the gaseous water and converting it into liquid water. That is our system. In that particular process then, heat has to flow out of the system, so therefore that's going to be an exothermic process. Okay. Lastly, ice cream melting. Ice cream melting. You can imagine then this is solid water. This is ice. melting into liquid. Okay, so essentially that's what we have here, and so we talked about that already. That's going to be an endothermic process, very similar to the boiling of water. Okay, all right. Let's do a couple more here, folks. Let's do a couple more here, and just to give you a chance to practice this. Okay, let's do then this problem right here. Take about a couple minutes here to work on this problem here and answer the question. Okay, this time essentially it's asking the same question. Okay, define the system, surroundings, and then direction of energy transfer simply means then does energy flow into, which is an endothermic process, or out of the system, which is an exothermic process. Okay, so go ahead and take a look at this, and let's go ahead and work this one out. Okay, okay, let's go ahead then, and I'm going to do the same thing. Let's go ahead and draw our box. Let's go ahead and do that. Draw our box, and then let's determine then system and surroundings. I'm going to go ahead and draw the box here. So we can use the box right there. There is whatever falls inside that system. Inside that box would be what we refer to as our system. So in the very first one, we have methane burning in a Bunsen burner laboratory. What is happening? What is the event that we are observing here? Or what is the phenomenon that we're observing here? Well, we're observing the burning of methane. The burning of methane, which is the combustion of methane. So our system here then is going to be the combustion of methane, which is going to be CH4 plus O2, give us CO2 plus H2O. That is our system. Okay, and that's simply it. That is our system. The surroundings then is everything else around it. Everything else around it. The room, the space around it, the school, the everything, the state, the world, the universe, the galaxy, everything else around this here then represents the surroundings. Okay. All right, so we're focusing our attention on this process here, okay? And so with that said then, there's always heat involved, okay? Heat involved in any process, because there's heat in the bonds here, there's heat here, and there's this potential energy stored up in each one of those, okay? So the question then is this, okay? Does heat then flow into or out of this system, okay? Well, when we do the combustion here, okay, we already talked about this. When we talked about combustion then, this initially you have to give it a little bit of heat. If you specify then at the very beginning of this process here, because methane and oxygen, when we turn on the Bunsen burner, folks, methane doesn't spontaneously combust. That doesn't happen. You have to give it a spark. You have to use a match. You have to use a lighter. We have to use the something to spark it. Okay, but once that spark is there, the reaction runs all by itself. And we talked about this reaction yesterday, and we saw then that this reaction is an exothermic reaction. It will produce heat, okay? And what it does with this heat is it will feed this heat back into itself. So it no longer needs any more energy to continue going because it generates its own energy. It's an exothermic process. It generates its own energy, and so therefore this reaction will continue to run so long as we have methane and oxygen. So as long as we have the reactants there, the reaction will run because it is an exothermic process giving off heat. Now this heat, obviously we feel also, we put our hands around the Bunsen burner, we feel that heat. So this reaction then gives off so much heat, it has enough heat left over to give off to the universe, okay, give off to the surroundings itself. So it uses some of that heat energy to continue going, but it also gives off that heat energy to the outside as well, okay, to the surroundings. So therefore, this is an exothermic process, okay? All right. Let's go ahead then, and let's take a look at the second one. Let's take a look at the second, and let me erase this here. Whoops, sorry. Let's go ahead and take a look at the second example. Okay, let's take a look at the second example here, and let me go ahead and, whoops, I lost my pen here. Sorry, see what's going on. Let me go ahead and draw the box here again really quickly. Okay, so there is our box. Let's go ahead then and describe what we have. Water drops sitting on your skin after swimming, it evaporates. Okay. We're talking about the evaporation of water here, folks. So the system this time then is going to be liquid water converting to water vapors again. This is not boiling, but this is evaporation. We learned back in the first year chemistry that evaporation is the vaporization of water, but it occurs at the surface of the liquid water itself. Okay, so this is evaporation here. Okay, and so with that said, then is the evaporative process exothermic or endothermic, which means that does it have to absorb heat or does it give off heat? And again, we talked about this, the vaporization of water requires then that heat gets put into the system from the surroundings. So heat has to flow in. So therefore, this is going to be an endothermic process because heat is needed in order to change liquid water into gaseous water. Okay. All right. Very good. Let's go ahead then and let's do a couple, one more, just to make sure we get this done. Okay. Okay. So we have then hydrogen and oxygen reacting to form water. Okay. Um, there's the reaction that occurs then. Okay, we have a violent reaction that gives off a lot of heat, and we saw this then. Okay, and so the question then is, well, which one is going to be lower in energy? Okay, a mixture. So the hydrogen oxygen mixture or the water itself. Okay, so let's go ahead and work on this together. Okay, let me go ahead first and foremost. Let's draw our system surrounding box. Okay, there is our box. Okay, and so let me ask you to consider this. Okay. What is the system that's being referred to here? Well, the system then is the reaction between hydrogen and oxygen to form water. Okay. Now, I had pointed this out to you. This is a reaction that generates a whole lot of heat. This is a tremendous amount of energy that is being released in this regard. Okay. So therefore, then, we consider this heat in the system is going to flow out. This is an exothermic process. This is an exothermic process. Okay? And being an exothermic process, we talked about this already. Being an exothermic process, energy is going to be released, which means then the product then is going to be at a lower energy state. Remember, the potential energy, and this is what we started out the session with today. The potential energy is going to be lower. The potential energy of the system is going to be lower, which means then the hydrogen and oxygen start out at a higher energy level, okay? And when they form water, water then has a lower energy level. So you can imagine this, hydrogen and oxygen will start out at a higher energy level here, and then what happens is as we go through, okay, water then will sit at a lower potential energy. This will always be the case here. So energy will increase. Okay, energy increases as you go up. And this will always be the case when you have an exothermic reaction. Heat's going to be lost, energy is going to be lost, and heat energy is going to be lost. And when that's the case, then the product will always be at a lower energy state than the reactant. Okay, so therefore, potential energy will always be lower for the reactant than with the product itself. Okay. All right. Very good, folks. Let's go ahead then and let me go ahead and save that. Okay, and let's continue on with our discussion. Okay. So water will be at the lower potential. So with that said, then we need to figure out then how we can use this to our advantage. Okay, what are there some patterns that emerge from this one? Okay? And first of all, the answer is yes. Okay, we can determine then the nature of the energy loss, energy gain. Okay, because the overall energy of the universe, and we were talking about this, has to be constant. The energy that we find in the universe, throughout the universe, what we started out with at the very beginning of time to where we're going to end up at, the energy will always be constant. What that energy looks like, the form of that energy is going to change. Obviously, it's going to change, and towards the end, we'll talk about this in chapter 17. Towards the end, all that energy is going to, one theory states that all that energy is going to be converted to heat energy. Okay? But until then, the form of that the energy takes then is going to be different, but the amount of energy will always be the same. And that's going to be what that is summed up in what we refer to as first law of thermodynamics. It states then that energy is constant. Okay, therefore then the energy and the energy of a system will also be constant. Okay, because energy you start out with in the system and the energy you end up with has to be the same. Okay, and because the energy of the universe has to always be constant. Okay, okay, and so that's what we have right there. And so we can talk about then so if we consider then the energy that within a system then, okay, and so we'll talk about this and we'll refer to this as internal energy. Okay, the internal energy then is going to be defined then as that change in energy. Any system then is going to change its energy, okay, but that energy change will have to be the same. Okay, the energy before and the energy after has to be the same. Okay, the energy before and the energy after the energy of the reactants, what you start out with, the energy what you end up with is going to be the same. Okay, but the change in energy for a particular system then will either be positive or negative. Okay, energy is going to flow out of the system or going to flow into the system. So the overall energy of a process will have to be the same. So with that said, then what we're going to do then is we're going to talk about the energy. We're going to define that energy in terms of work energy and heat energy out of time here. But what we'll do then is tomorrow, we're going to pick up with this. And your exam then, again, remember, will only cover through what we will be able to talk about tomorrow. My hope is that we can talk about spontaneity tomorrow, but it will not cover everything in Chapter 6, and it won't cover everything in Chapter 17. It'll only cover what we discuss here in class, okay? All right, so with that said, then I'll pick up with this discussion tomorrow with internal energy and how we calculate for it, and then we'll hopefully get to spontaneity tomorrow, okay? All right, folks, have a good day, and I will see you tomorrow.